Hey everybody, welcome to Howlin at the Moon Science Friday number 5. This week we got a topic that I'm really excited about. Not only the subject matter itself, but the way that it came about. We're going to talk about relativity this week. And the way that this came about was a friend of mine who's a fan of Howlin at the Moon, watches all these broadcasts and follows me on social media, saw something that I posted on social media this week from one of the science feeds that I follow. I posted an article that discussed the reason that the center of the Earth is actually younger than the surface of the Earth. Now, when I posted this up, there were a couple of reactions to it. One was that, boy, I don't understand a word you just said, that kind of thing. And the second reaction was, well, yeah, it makes sense to me, but for reasons that weren't the right reasons. It doesn't have anything to do with the fact that the center of the Earth came first and then accumulated matter on the outside. That's not the way that it happened. It has to do with general relativity, which is something, of course, that was developed by Albert Einstein. It's what he's most famous for. So that's what I want to speak with you about this week. We're going to talk about relativity a little bit and why it makes the inside of the Earth younger by 2 years, it turns out, than the outside of the Earth. So let's get into it. Now, Albert Einstein developed his theory of relativity in two parts. He developed something called special relativity first, and special relativity deals with relative motion. And then after that, he tackled general relativity, which deals with gravity. And that was the tougher of the two, which is why he developed it second. So whenever you're talking about relativity, there are two postulates of relativity. A postulate is just a fancy way of saying these are kind of the ground rules or the general assumptions along which we're operating when we talk about this topic. The first of which is that the laws of physics are the same in all inertial frames of reference. Now, what that means is that as long as there are no accelerations present, acceleration means speeding up, slowing down, or changing direction. As long as no accelerations are present, I can do a physics experiment in any frame of reference and I get the same results. There's a corollary to that, which is kind of fascinating, which says that all inertial frames of reference are equally valid, which means that you can't tell the difference in a physics experiment between something that's at rest and something that's moving in a straight line with constant speed. There is no experiment that you can devise that shows the difference between those two, because there isn't any difference between those two. All motion is relative. That's what Einstein said, is sort of a succinct way of saying this. You can detect acceleration, but you cannot detect constant motion in a straight line with no change of direction. Now, the second postulate of relativity in general is that the speed of light, which is something we denote with a little c in physics, it's about 186,000 miles per second, or 3 times 10 to the 8th meters per second, just a little bit less than that. That's a constant, and it is regardless of your frame of reference. So all observers in any frame of reference see the speed of light as being the same. Now, that's kind of interesting because that is a big difference between Newtonian and Galilean thinking. According to Einstein, if I'm standing still and I turn on a flashlight, that beam propagates forward at 186,000 miles per second, or 3 times 10 to the 8th meters per second, whichever you prefer. But you know what? If I jump in the back of a pickup truck and I drive down the road, standing in the back of an open pickup truck, put the flashlight over the cab, shine it forward, the beam does not propagate forward at 3 times 10 to the 8th meters per second plus 100 miles an hour. Nope, it's still 3 times 10 to the 8th, or 186,000 miles per second. So the speed of light doesn't change depending upon relative motion between observers. Now, without some arithmetic, I can't really justify this to you, and we don't want to do that here. We want to keep this in words and sentences. So you're going to have to take some of what I tell you just on faith. But I will tell you this. No serious physicist quibbles with anything that I'm about to tell you. Einstein's theories of special and general relativity are hugely successful theories. They're cornerstones of 20th century physics. And in fact, general relativity had one of the fastest tests ever. Literally within days of Einstein publishing general relativity, there have been all these experiments proposed to test it, and you can verify general relativity to as many significant figures as you want. It just works. Everywhere we look in space, we see the effects of special and general relativity. And again, nobody quibbles with any of this. Doesn't mean we understand everything that we see in space, but this part of it we have pretty well figured out. So when I talk about a theory, I'm not talking about some harebrained idea that may or may not be true. In physics, a theory is something that's generally accepted to be true and has a lot of evidence that supports it, like the theory of gravity. Nobody disputes that gravity works. So what happens in relativity is that something called time dilation. Time dilation is a fancy way of saying time slows down. Now, we tend to view time as being linear. It's the same everywhere. Clock ticks the same way no matter where you put it. Well, the reason that we perceive reality that way is because we don't spend a lot of time operating at significant portions of the speed of light. We don't operate in areas where there's a big difference in gravity between point A and point B. Everything we do is on the surface of the Earth, where the force of gravity is roughly uniform over the whole surface of the Earth. And even if you go out into space a little bit, it's not that much different. Gravity doesn't fall off that fast. It's an inverse square, so you have to go way out into space before gravity falls way off. So our senses just haven't evolved to perceive relativistic effects. But with the modern instrumentation, you can see them all the time. You can put a precise clock on even a fast airplane, and you can detect time dilation. You can measure it. So again, time dilation just means that time slows down. And that can happen for two reasons. The first is relative motion between an observer and between two observers. They would each observe each other's clock is running more slowly. Now, you have to get up to a fairly significant portion of the speed of light before these effects become easily discernible. But you can measure them even when you're not traveling at significant portions of the speed of light. As I said before, you can measure it in an airplane. That's fast enough. Now, it turns out not only does relative motion cause time dilation, but so does big differences in gravity. So if the gravity is stronger at one point than it is at another point, the place where the gravity is the strongest is where time runs most slowly. Now, that leads to something called space-time, and there's a couple of illustrations up here that'll show you what space-time's all about. The way Einstein viewed space-time, and space-time means that space and time are woven together. They're not separate entities. They're a part of each other, and you really can't separate them. You can describe them separately, but they're part of the same fabric of space. And what Einstein said is you can think of space-time as like a bed with a sheet laying over top of the mattress. And if I place heavy objects on that sheet, it puts divots in that mattress. The heavier the object, if I do a tennis ball, the divot's not very big, but if I do a bowling ball, I start to get a bigger divot, the more massive the object. That's a warping of space-time due to gravity, and those are called gravitational wells. A way you can think of gravity is if I put a marble on the edge of one of those little divots created by putting a bowling ball in a blanket, the marble will roll right down until it comes into contact with the bowling ball. You can think of gravity as operating that way. Well, it turns out the deeper I go into that gravitational well, the more time is dilated, which means it runs more slowly. So, time dilation can be caused by one of two things, relative motion, or it can be caused by going deeper into a gravitational well. Well, where's the gravitational well deepest on Earth? It's deepest at the center of the Earth. And it becomes, I rise up the gravitational well, time starts to run faster and faster. So it runs most slowly at the center of the Earth. It starts to run faster as I rise out of that gravity well, which means that there is a slight difference in how fast time moves between the center of the Earth and the surface of the Earth. We're talking about nanoseconds per year. But over a 4 billion year lifetime of the Earth, that adds up. And that is the reason why time indeed runs more slowly at the center of the Earth than it does at the surface of the Earth, which is why the center of the Earth is a couple of years younger than the surface of the Earth. That's the reason why. Now, a really extreme example of this same effect is the event horizon of a black hole. The event horizon of a black hole is a singularity in space because it's a place where time dilation becomes infinite. So time actually stops. Now, black holes are a subject for another Science Friday, but the event horizon of a black hole is a place in space where the gravity beyond that event horizon, inside the event horizon, is so great that it exceeds light speed. So the escape velocity of light is exceeded. So light can't climb out of that gravity well. So as you approach the event horizon of a black hole, time runs more slowly, more slowly, more slowly. And when you finally get to that event horizon, time stops. So if you were to get sucked into a black hole, among the other unpleasantries that you would experience, you would be frozen in time forever at the event horizon of the black hole, because time would stop for you at the event horizon of the black hole. All right, so that's all there is this week. I don't want to get into it too much more. Fun topic, very fascinating. And as always, if there's something that you want to hear about on Science Friday, you be sure to let me know, and I'll be seeing you. Cheers.